faithfully conveying value by interpreting great books from around the world. Hello, this is Sally's Book Talk. Today, I'll interpret the book, The Trouble with Physics. Physics is the foundation of all natural sciences. So, what's the trouble with physics? The book states in the preface that since the 1980s, progress in physics has stalled. No real advances in fundamental theories, and our understanding of the world's essence remains stuck in the framework built by Einstein, Bohr, Schrödinger, and other older physicists. Why is that? The English edition of the book has a subtitle, The Rise of String Theory and the Fall of Science. The author believes the problem lies in a flaw in cutting-edge research, the famous string theory. String theory is considered a theory that could unify everything in the cosmos.
With ideas like multiple dimensions and parallel universes, it's captured people's imagination and won over many physicists.
But this book goes against the mainstream, questioning string theory and arguing it's a major cause of physics stagnation. Its author, Lee Smolin, is a renowned American theoretical physicist, one of the founders of quantum gravity, and hailed as one of today's most original thinkers. Using his firsthand experience from researching string theory, he demystifies it for us. He argues that this elegant theory has caused problems for physics, and his bold questioning has gained support from many physicists. Roger Penrose, the 2020 Nobel Prize-winning British physicist, commented that Smolin's critical judgment is spot on. He said string theory is responsible for the lack of real progress in fundamental physics over the past 25 years, a statement worth deep thought. Now, I'll break down the book into 3 parts. First, what's the development history and basic idea of string theory? Second, how string theory has influenced research in cutting-edge physics. Third, where should the future of physics head? Before diving into these questions, let's first examine what troubles physics is facing. The book was published in 2006. The author believes the period from 1980 to 2006 was the most frustrating. For 25 years, fundamental physics theory saw almost no progress. But looking back over 200 years, key breakthroughs happened roughly every 25 years. From the wave theory of light, the discovery of electromagnetic phenomena, the second law of thermodynamics, to the proposal of relativity, quantum mechanics bursting onto the scene, and the discovery of thousands of particles, new ideas were constantly emerging. They were tested and confirmed. But ever since the standard model of fundamental particles was established in the 80s, physics has come to a standstill. A top theoretical physicist in particle physics, Mark Wise, said at a seminar in 2006, "If I had to discuss the mass problem of particles now, I'd probably run out of things to say by the 1980s. Over those 25 years, it wasn't that no theories emerged, quite the opposite. This period gave birth to the most popular and attention-grabbing theory, string theory. String theory nearly monopolized cutting-edge physics research for those 25 years, and it's also a regular feature in popular science books and sci-fiction novels. Many people mistakenly view string theory as a confirmed scientific theory, but in reality, it hasn't been experimentally verified to this day. So, Nobel laureate Dutch physicist Gerard Hoof stated, "I'm not ready to call string theory a theory yet. It's more like a model, or even just a hunch." To summarize the trouble with physics, from the early 1980s to 2006, over nearly 25 years, theoretical physics stagnated under the dominance of string theory. I have To explore the reasons, we first need to understand what this string theory that has swept through physics for years actually is. Now, let's dive into the first part, the development history and basic ideas of string theory. The story begins in 1968 when, at CERN, a 26-year-old Italian physicist named Gabriele Veneziano noticed an interesting phenomenon related to the Euler function. Particle collisions generate massive data with surprising correlations to the function. The The complex curves described by string theory seem to accurately correspond to certain properties of particles. In this view, particles are no longer points, but can be seen as one-dimensional curves that stretch like rubber bands and vibrate in different modes. Each represents a different particle. In 1970, several scientists from the University of Chicago, Stanford University, and the Niels Bohr Institute almost simultaneously discovered the physical significance of the Euler function. Some felt that this theory describing particles with vibrating curves might be nicknamed the rubber band theory, but that name wasn't elegant enough, so people ended up calling it string theory. This highly imaginative theory wasn't well received at first. People discovered that for this theory to align with special relativity and quantum mechanics, it had to meet several conditions. First, there should exist particles faster than light. Second, there should be a new type of massless particle. Third, the universe must have 25 spatial dimensions. These three conditions, each more implausible than the last, had no data to support them. Amid widespread disappointment, physicists worldwide discarded string theory. Only a few, like Shirk, Schwartz, and Green, refused to give up.
They felt the mathematical beauty revealed by string theory was truly astonishing.
So they began continuously refining this fledgling string theory. After over a decade of effort, by 1984, string theory had finally been transformed.
It evolved into a brand new theory called superstring theory, sparking the first superstring revolution in physics.
Superstring theory doesn't mean superior string theory. This super refers to a physical theory called supersymmetry. So what is supersymmetry? Based on particle spin, scientists classify particles into fermions, like neutrons, protons, electrons, and bosons, like photons, gluons. Supersymmetry means every particle has a partner. Fermions have boson partners, and bosons have fermion partners. When scientists applied supersymmetry to string theory, magic happened. Those three problematic conditions were suddenly resolved. First, the theory no longer required faster-than-light particles. Second, and superstring theory's most exciting achievement, people discovered that the predicted massless particle was actually the graviton, which transmits gravity. For years, what troubled physicists most in unifying fundamental forces was gravity's incompatibility with quantum mechanics. But superstring theory emerged, seamlessly incorporating gravity into quantum mechanics and unifying all forces, including gravity. By unifying all particles as vibrating strings, it brought together all forces and particles in the universe. Isn't this exactly the unified theory of everything that scientists have been pursuing?
Now there's just one last issue: those 25 spatial dimensions. Superstring theory reduced them to 9 dimensions, much closer to our three-dimensional reality.
So, how do we explain the extra 6 dimensions? Physicists found a solution in mathematics by introducing a model called Calabi-Yau space, which powerfully explains the 6-dimension problem. Let's explore this. Back in 1954, Italian mathematician Eugenio Calabi proposed a conjecture predicting the existence of a compacted space structure, twisted and folded like a crumpled paper ball. No one believed this strange prediction, yet no one could disprove it. Later, a 21-year-old Chinese-American mathematician, Xing-Tong Yao, resolved to crack this long unsolved problem. He initially aimed to disprove the conjecture, but after extensive calculations in 1976, he reached the opposite conclusion, mathematically proving such a 6-dimensional space exists. These dimensions are compacted into an incredibly tiny space, with a radius just a billionth of a trillionth of a proton's radius. And
This became the famous Calabi-Yau space, essentially tailor-made geometry for string theory that revolutionized physics.
so, in string theory's 9-dimensional world, 3 dimensions form our reality, while the other 6 are curled up in Calabi-Yau space. If you were inside this 6-dimensional microspace, it'd feel mind-bending, so twisted that straight lines don't exist. Looking forward, you might see your own back. If you tapped someone's shoulder ahead, you'd find a hand reaching from behind to tap your own shoulder. That's superstring theory, the first string revolution that completely won over physicists. Even former critics embraced string theory, but after another decade of research, something unexpected emerged. 5 different versions of superstring theory. And all 5 versions are mathematically consistent. Now it's awkward. The theory meant to unify everything is itself divided. Thus, in 1995, the second superstring revolution erupted, spearheaded by the field's absolute leader, aiming to unify string theory itself. American physicist Edward Ritten discovered that although these 5 versions seemed to describe 5 different universes, they actually described the same thing. In physics, when 2 different ways explain the same phenomenon, we call it duality. Like a couple where the husband thinks his wife is too domineering, while she complains he's too timid.
Well,
Their descriptions differ, but mutually reinforce each other. We can say their dialogue is dual to each other. So these 5 theories are just 5 manifestations of one true form, unified by written in higher dimensions. He increased spatial dimensions from 9 to 10. Thus, this unified superstring theory revealed an entirely new picture.
Here, not only strings exist, but something else too, brains, which are 2-dimensional surfaces.
Like strings, they move freely in space, and in higher dimensions, there are even 3D, 4D, up to 10D brains. Our universe is a 3D brain floating in higher dimensional space. These brains vibrate and oscillate like strings.
In this theory, strings can be seen as one-dimensional brains. Ritten named this unified superstring theory M theory.
All right, that covers the development and core ideas of string theory. Now, back to the book's central question. Why has string theory caused such confusion in physics? Next, we'll explore part 2, how string theory influences cutting-edge physics research. A saying in physics circles goes, string theory is 21st century physics accidentally landing in the 20th century. At Harvard workshops, it's called postmodern physics, highlighting its super-forward nature. This chose man's head creates a problem. Experiments can't keep pace with theory.
Why do we say this?
Mainly because string theory heavily relies on mathematics, treating mathematical structures as research subjects, then deriving physical facts from math. This often creates mismatches between models and reality. The author says if traditional physics was a physical soul wearing mathematical clothes, string theory is like a mathematical soul hovering over physics, unable to land. And then, so many know string theory requires higher dimensions, but few understand where these dimensions come from. Actually, this was derived from mathematical equations, as explained by a leading figure in string theory. American physicist Brian Greene explains it this way. In string theory equations, there's a troublesome mathematical expression that would produce problematic physical phenomena. This expression is multiplied by a coefficient, d minus 10, where d represents the number of space-time dimensions. To eliminate this trouble, we set d equal to 10. 10 minus 10 equals 0, and 0 times the trouble makes it vanish. That's how we get 10-dimensional space-time. Subtract 1 time dimension from 10-dimensional space-time, and you get the 9 spatial dimensions of superstring theory. So higher dimensions are purely mathematical constructs. But having a mathematical model doesn't establish a physical theory. It needs verification. So far, there is 0 evidence proving string theory correct. First, string theory can't make scientific predictions. Only theories that accurately predict facts become scientific laws. String theory falls short because it has countless mathematical forms. We don't know which corresponds to our universe. Take the Calabi-Yau space we discussed earlier. It's a purely mathematical model. If there were only one Calabi-Yau space, we might get a definitive string theory. But mathematically, no one knows how many such spaces exist. Xing-Tung Yau himself said, at least 100,000 spaces exist, each with completely different physical laws. For instance, in some universe corresponding spaces, Light speed might not be 300,000 kilometers per second. And how can a theory without uniqueness predict or explain our world? 100,000 is actually a small number. In the grand design, Stephen Hawking said the theory predicts 10 to the fifth power universes, each with unique physical laws, only one matching ours. This number exceeds all atoms in the observable universe. Surely, among all these universes, one must satisfy our physical laws. This makes string theory incredibly hard to disprove. Conversely, we can't possibly examine all possibilities to find that one unique universe. Second, string theory is nearly impossible to observe because strings are unimaginably tiny. To illustrate, if an atom were scaled to our solar system, a string would only be as big as a tree on Earth. Theoretically, we could observe such tiny strings by accelerating particles to sufficient energy levels to probe deeper into the microscopic world. Oh, but this is only theoretically possible. Because with current technology, we'd need a particle accelerator the size of our Milky Way galaxy, like the sci-fi galactic accelerator, to observe the string world. So currently, it's safe to say our generation, or even several generations, likely won't live to see it. String theory verified this way. The author points out that string theory has developed for nearly 30 years. Since the 18th century, no major theory in scientific history has persisted this long without either declining or gaining experimental support. Nobel laureate Sheldon Glashow once compared superstring theory to the Star Wars program, as both consumed massive resources without real-world testing. He even tried to block string theory at Harvard, though unsuccessfully. Of course, we shouldn't dismiss explorations without breakthroughs as useless, nor reject string theory outright. And the core issue isn't whether string theory is worth pursuing, but how a theory without predictions or experiments monopolized fundamental physics resources. Behind the theory lies a bigger problem: human factors. This has hindered physics progress more severely than string theory itself. Now let's examine what's gone wrong with scientists researching string theory. The author believes string theory nearly monopolized fundamental physics research directions, stifling other theories. This is no longer a scientific issue, but a sociological one. It reveals an uncomfortable truth. Science isn't entirely objective or rational. First, in the US, studying string theory became a trend. Scientists bucking this trend struggled professionally. The author notes that in physics departments at top universities, Berkeley, Caltech, Harvard, MIT, Princeton, Stanford, between 1981 to 2006, 20 of 22 particle physics tenure-track professors specialized in string theory. String theory dominated academia. Young theoretical physicists avoiding this field essentially ended their careers. As of 2006, when this book was written, except for a Penn State research group, no assistant professors working on quantum gravity without string theory or higher dimensional foundations were hired by U.S. research universities. Even in fields like cosmology, with little connection to string theory, researchers often claim their work will eventually be derived from string theory. Second, string theory research lacks diversity and heavily depends on authoritative thinking. University postdoc selectors found that in fields like cosmology and quantum information, proposals were as diverse as the candidates. Unprecedented intellectual variety. But in string theory, identical research plans kept recurring. The entire field operated under a few senior professors' ideas and frameworks. From 1996 to 2006, only 2 young string theorists made field-altering discoveries. Most researchers cautiously followed academic authorities, making the field increasingly narrow and homogeneous. Third, some string theorists ignore limitations while exaggerating achievements. For example, many popular science books directly call the theory of everything, presenting conjectures as facts.
The author even saw conjectures labeled correct but unproven. Astonishingly, this became widespread.
Dutch physicist T. Hooft critiqued string theory. It's like me giving you a chair but saying the legs are missing and cushions are coming later. Then what have I actually given you? Can it still be called a chair? American physicist Richard Feynman explained why he resisted the string theory trend. I dislike how they don't compute or test ideas, inventing explanations for anything contradicting experiments. Fourth, a clear divide exists between string theorists and others. They ignore or outright reject alternative theories. Slack physicist Hewitt noted, string theorists have excessive superiority. They genuinely believe other theories should yield. Nobel laureate American physicist Subramanian Chandrasekhar loved to tell this story. Once, he encountered a young string theorist who advised 70-something Chandrasekhar to abandon his work and switch to string theory or risk becoming obsolete like those who ignored quantum mechanics in the 1920s.
The elder scientist replied, "Young man, I knew Werner Heisenberg, founder of quantum mechanics. He'd never recklessly tell people to stop their work for quantum theory, nor rudely declare,
A man who earned his doctorate 50 years ago was becoming obsolete. Having outlined these issues with string theorists, the author stresses this isn't personal criticism. In truth, many string theorists are accomplished physicists, humble and troubled by these group dynamics, who agree the situation is problematic. Strangely, why does a group of well-intentioned individuals with sound judgment collectively act so absurdly? Oh, the author believes this transcends science. It's a sociological issue. Yale psychologist Irving Janis coined the term groupthink in the 1970s, defining it as a conformity-seeking mindset. When people join tight-knit groups, they compromise their judgment to maintain unity. Maintaining group dynamics in science operates under the same social forces as other human endeavors. Scientists weigh senior authorities' influence, choose theories securing funding, and consider job security. Conforming maximizes personal gain. Even when privately disagreeing with the approach, the author recounts friends warning him, "The group decided string theory is right. You can't fight sociology. Science is human action, subject to human flaws. Changing physics is tomorrow's mission." So what can scientists do? Now we'll explore part 3. Where should physics go next? Answering this requires returning to science's essence. The author says, some hope to establish a universally applicable methodology for scientific activities, but perhaps no such universal method exists. Why is this so? The author offers an analogy. Scientists are like blind people, seeking the highest peak. Though sightless, they can sense uphill or downhill paths and measure height through sound. When they reach a peak and find all paths slope downward, can they conclude they've reached the highest peak? No, because multiple peaks exist. They might be on Mount Tai rather than the Himalayas. For the blind, confirming the highest peak is extremely difficult. Now, thus, we can't discover a universal formula for scientific success. Science advances through trial, with successful strategies emerging opportunistically, even randomly. So, just as the blind can't grasp the full mountain landscape, scientific exploration always yields incomplete information. This creates two problems. Excessive caution breeds distrust and paralysis, while reckless advancement leads to deviation without awareness. Therefore, we need both types of scientists. The author metaphorically calls them visionary prophets and skilled artisans. Prophets represent broad-visioned innovators, tradition disruptors. Artisans signify technical experts adept at experiments and problem-solving, tradition maintainers, and refiners. During normal science periods, artisans refine theories through standard experiments. When theories fail, new experiments, scientific revolution begins, requiring prophets to navigate the darkness. For example, early 20th century thinkers like Einstein, Bohr, Schrödinger, and Heisenberg were milestone-setting prophets. They created frameworks for general relativity and quantum mechanics, whose refinement demanded extensive technical work. Thus, subsequent generations of physicists became artisans, gradually building details into the quantum physics standard model. With the establishment of the Standard Model, normal science has again reached its limits. We need to enter a period of scientific revolution once more.
It's precisely at this juncture that physics encountered problems.
It lacks true prophets at this stage. The issue with string theory is the problem is that it's artisans attempting prophets' work. They excel at calculations and model building, but lack deep contemplation of the universe's essence. At first glance, string theory seems avant-garde, bold, and imaginative, appearing to break through normal science. But it's too detached from physical phenomena to make testable predictions. A theory without verifiable predictions never fails, but can never succeed either. And now the path is clear. To transition physics from normal to revolutionary periods, we need more prophets and environments nurturing genuine visionaries. The author proposes 3 recommendations. First, welcome independent thinkers who challenge mainstream research. Prophets often face exclusion for nonconformity. We should reserve university positions for them, letting their ideas ignite students' minds. Second, reform peer review to give diverse research freer growth space. Peer review means some scientists judging others. Evaluators are almost invariably older and more powerful. Without dismantling this hierarchy, young scientists must cater to seniors, turning science into driving with brakes slammed. M8. Third, adjust resource allocation to fund more high-risk research. Funding typically supports low-risk, low-reward science. Science should adopt strategies from tech firms and investment banks. Reserve funds for high-risk, high-reward projects. Without adventure, how can revolutionary breakthroughs happen?
Especially when the reward is uncovering the universe's secrets.
These 3 points might seem unremarkable. Haven't scientists noticed these issues? The author notes this is precisely what makes the problem severe. When the author wrote about these issues for a journal advocating reform, the article was rejected.
The author was furious. Were the editors suppressing different voices?
But the reason was exactly the opposite. The editor told the author that these issues had already been widely discussed in social sciences and humanities and were common knowledge. Only then did the author realize that the scientific community was still turning a blind eye to these problems. In terms of academic governments, natural sciences have fallen far behind humanities. The problem is far more serious than we imagined. That covers the main content of this book. At the end of the book, the translator mentions an issue widely debated by Western scholars. When thought changes your mind, that's philosophy. When God changes your mind, that's faith. When facts change your mind, that's science. So, is string theory science, philosophy, or faith? The very act of posing this question shows that string theory is no longer entirely fact-based.
Science should return to the path of seeking truth from facts, and no theory should monopolize the field before being proven.
In 2006, John Schwartz, a founding figure of string theory, stated that string theory might not be completed even in another 100 years. Over such a long period, let string theory step down from its pedestal and develop equally with other theories, fostering a diversity of ideas. This is the necessary path to resolving the troubles in physics. All right, the trouble with physics. That's the end of this book interpretation. Reading notes are below the audio. We'll see you next time.